I'm here to present you the Octopi project. So it's financed by SSF. So I'm going to divide the talk in 3 parts: the spirit of the project, and then rather than show you all the things, amazing things that we have done, I choose like 2 highlights that I would like to tell you about it. One with the industrial impact, and another one which is the most recent project that I'm excited about within Octopi. All right, so yeah, Octopi focuses on developing programming languages for making the IoT, the programming of IoT devices secure. Okay, and we know that IoT is super hard to program with. There's plenty of security problems because of the diversity of the different operating systems that are around, different protocols, et cetera, et cetera. So in the project, we try to give root causes that if we deal with them, we can really improve the security of programming IoT devices strongly in the right direction. So yeah, so one of the root problems is the lack of the security expertise. People usually developing IoT software are not security experts, right? They know how to program IoT devices. They need to use low-level programming languages because you need to be close to the hardware, control all the memory bits that you have. And there is no system-wide control on what is happening when many devices interact with each other. Okay? So can we do it with all of these root causes at once, right? And our mission is, yes, we can do that. We have done quite a lot of work on that direction using programming languages technologies, right? Programming languages that make visible to the programmers what are the security concerns, what are the resources concerns that you have, and what are the interaction with other devices that you might have, okay? So we propose to use high-level languages, because if you use high-level languages, as I said before, you can make explicit, you can remove using details about memory bits and so on. You can focus on more business logic of the application. Then you can make explicit the security concerns when you program, and as well, all the interactions that you might have. Of course, if this was that easy, why nobody has done it before, right? What is the main challenge of this project? Is this arrow. How you push high-level languages, guarantees, and abstraction into embedded constrained devices. That's kind of the challenge. And the way we address that is twofold. So this is how Octopi works. At Chalmers, we are great developing languages for different purposes. So we have the blue part, where we play with different languages for different things, data privacy, information flow control, resources testing. And once we design that language, then we push it down into IoT devices following 2 paths. The programming language that we develop generates code, low-level code, like C, in an automatic fashion. You compile that, and then you run in the device. Or we design a virtual machine that fits in the IoT device and can interpret this high-level language, right? This is the orange and the green part, okay? So last year, when I was here, I was presenting different stories or different results on both tracks. Today, as I said before, I'm going to focus on 2 highlights. And the first one is about a language that we developed related with data privacy. So we want to collect information from IoT devices. And usually that information is generated by human behavior, right? And encodes a lot of your habits in your private life. How can we perform analytics and learn from that data without exposing the privacy of the users? Okay? So we created a language. That language is called Dipela. That does precisely that, allow you to process data with personal information, but in a way that when you observe the result of that processing, you cannot point fingers to see who was in the data set. Okay? But still you can learn from the population, from the whole users. So this result was published in the top-tier conference, Security and Privacy 2020. This is one of the most top-tier conferences in security. And we created a spin-off company with the same name, Dipela, that aims to, or is targeted to push the research that we did in this project into industry, right? So, and this year, so we run a paid proof of concept with Ericsson. So, and we succeed. We were super happy with the collaboration. Ericsson was super happy with the collaboration, and they even invest time in writing an article about that collaboration. Okay. Let me show you the use case. So you see, like, we started this idea of Dipela for collecting information from IoT devices, but we use it completely different when we interact with Ericsson. And this is a use case. So we have a car manufacturer that wants connectivity, and Ericsson sells that connectivity to the car manufacturer. Okay? And Ericsson has contracts with different telecom operators across whole Europe, right? But Ericsson would like to give to the car manufacturer information about how the network behaves. Okay? Where the peaks are, where the flats are, but it doesn't want to reveal which operator was down at a certain time of the day. So here is not the privacy of a person, it's the privacy of how the operators work, right? Because Ericsson is not there to evaluate the performance of the operator, it's just to provide insights about the network connectivity to the car manufacturer. Okay? So we use Dipela for that. Yeah, and it turns out that in this scenario, it could help Ericsson in developing the products about the connected vehicle. All right. So the second highlight that I want to show you today is related to one of the latest programming languages we are working on, and this is related with information flow control. Information flow control is about having a tight control how data moves in your application, how your secrets are being handled. When your secrets reach some unauthorized place, you should raise an alarm right away, okay? And you would like to see that in the code. When you write the code, you would like to that the compiler tells you, look, here you might be sending a secret over the public network, and that's not okay, okay? So, yeah, so we are developing a programming language for confidential computing. Confidential computing is this idea of having a clean room where participants can put data in. Nobody can see what happens inside the clean room. You can process the data and take out the results, okay? And this is using what we hear before here, HGX or another trusted execution environment, okay? So our contribution in this space is the following. And there is a poster outside with the students working on this, is to develop a programming language. You can see there are three colors, green, red, and yellow. You program just thinking about trusted execution environment or not trusted execution environment. And you program about having a value in your program that moves between different parts of your application. And we automatically will take that code and split it in the code that goes in the trusted execution environment and the code that goes outside the trusted execution environment, outside the clean room, and we give you all the secure communications for free. The compiler will take care of that for you. And on top of that, we check that secrets are handled in the right way, that it never happens that what is outside the enclave might leak some information. All right, just to wrap up, these are the list of publications that we have. We can see top-tier conferences. We have like 2 top-tier conferences and 2 distinguished work. But besides publication, we have the tradition to release a lot of code about our experiments of languages, so someone else can try and play with them. So we can see there, in green, are code releases. And of course, I'm not alone in this project. I'm with all my colleagues, fantastic colleagues, and students that help me out to make the realization of Octopi a reality. Thank you very much.
Thank you very much.